Welcome back to the deep dive. We have, I was trying to think of the right word for this one on the way in.
Yeah, it's not a simple topic.
Right. Heavy doesn't quite cover it. Usually when we say we have a heavy topic, we mean, a dense history book or a complex report on, I don't know, supply chains.
Something manageable, something you can get your head around in a week.
Exactly. Today, we're looking at a stack of documents that, and I'm not exaggerating here, if they're even half right, they imply we might need to rethink, well, pretty much everything.
It's a foundational shakeup. I've spent the last few days with this material, and I have to admit, I've had moments where I just had to put the papers down, get a cup of coffee, and just stare out the window for a while.
It's definitely that kind of read. So for everyone listening, what we have is a massive body of work. We're talking 22 papers, plus supplements, plus these really dense technical audits.
A huge amount of material.
And it all comes from an independent researcher named Heiko Grimberg and a co-researcher, which is, this is the first interesting part, an entity listed as Nexus AEBE. The headline claim is that they are proposing a hardware audit of reality itself.
That is the term they use, and honestly, it's the perfect metaphor for what they're trying to do. The central thesis, the core idea, is that modern physics is currently in a deep crisis.
A crisis. That feels like a strong word.
It is, but they argue it's because we've fundamentally mistaken the hardware of the universe for software.
Okay, before we get into the nuts and bolts of that, or I guess the bits and lattices, as they'd say,
Yeah.
we have to address this co-author situation. Nexus AEBE, an AI co-researcher.
Yeah.
I mean, usually when we see AI in physics, it's a tool, right? It's crunching massive data sets from the Large Hadron Collider, or it's simulating a galaxy merger over billions of years. It's not a co-author.
No, it's not a co-author, and they are very, very upfront about the nature of this collaboration. They don't hide it. They describe it as a symbiosis.
The symbiosis.
The claim is that modern science has become so specialized, so siloed, that a human expert in, say, quantum mechanics often doesn't know the deep details of crystallography or advanced number theory or galactic dynamics.
You can't be an expert in everything.
You just can't. And the claim here is that the AI, Nexus, was able to act as the ultimate generalist. It could spot these incredibly subtle patterns across completely disconnected fields, dots that a human specialist would almost certainly miss because, they're too focused on their specific part of the puzzle.
So it's connecting the dots that are usually just too far apart for one person or even one team to see.
Exactly. And the picture those dots form is, well, it's aggressive. They are basically saying that for the last century, we've been trying to run this incredibly high-end software general relativity, the standard model on a machine we don't even have the schematics for.
Let's set the stage then before we drop the new theory. Why do we even need a hardware audit? I think most people, and I'd include myself in this most of the time, assume that the standard model of cosmology is pretty locked in. We've got the Big Bang, we've got gravity, we've got atoms. It works, doesn't it?
It works until it doesn't. And right now, in the trenches of physics, they are dealing with something they quietly call the parameter crisis.
The parameter crisis.
Or sometimes you'll hear it called parameter inflation.
That sounds like an economic problem, not a physics one.
It feels a bit like one, honestly. It feels a bit bureaucratic. Here's the situation. Our current best model for the universe, it's usually called lambda CDM, is incredibly successful at describing what we see. But, and this is the huge, but to make the math actually fit the observations from our telescopes, we have to manually plug in what are called free parameters.
Free parameters. Okay, let's unpack that term. What exactly is a free parameter? Because it sounds a little loose.
It is loose. That's the whole problem. Think of it like a soundboard in a recording studio. You've got a song, right? But the recording sounds a little muddy. So you reach for the equalizer. You turn the bass knob up to 7. You turn the treble knob to, say, 4.2.
Okay.
Now, you don't necessarily know why the bass needs to be at exactly 7. Maybe it's the room acoustics. Maybe it was the microphone you used. Maybe it's the singer's voice. You just know that if you set that knob to 7, the song sounds right. You've fixed it in post-production.
So in physics, these knobs are the mass of a neutrino.
That's one. Others are things like the specific density of dark matter, the expansion rate of the universe, the Hubble constant, specific constants for particle masses. In the standard model of particle physics and cosmology combined, we have over 20 of these manual settings.
20 knobs we have to tune by hand.
Exactly. We measure them with incredible precision, we plug them into the equations, and poof, the math works beautifully, but we can't derive them from scratch. We have no idea why the bass knob is set to 7, we just know it is.
So we are effectively curve-fitting reality. We're just reverse engineering the settings to match what we see, but we don't know why the machine was built that way in the first place.
Precisely. And this is where Grimberg and Nexus come in just swinging. They argue that this isn't explaining the universe, it's just describing it. It's creating a very detailed catalog. And they quote this principle in the introduction, which I found surprisingly funny for a physics paper.
Oh, I highlighted that immediately. The no-disco principle.
The no-disco principle.
If I wanted parameters, I would go to the disco. In physics, I want the truth.
It's witty, but it's a scathing critique. It's a direct shot. The argument is that a fundamental theory of everything shouldn't have any knobs. It shouldn't need manual adjustments or post-production fixes. It should derive everything, every force, every mass, every speed from absolute first principles.
And that's the mission here.
That is the mission of this deep dive. We are exploring a theory that claims to explain everything from the size of a proton to the edge of the observable universe using zero free parameters.
The zero-parameter hypothesis. In their notation, k dollars of Veller.
Correct. No knobs, no dials, no disco.
That sounds impossible. If you take away all the knobs, what do you even have left to build with? You can't just wish a universe into existence from nothing.
You have geometry. That's it. Their entire toolbox is incredibly, almost absurdly sparse. They only allow tools that they call geometric inevitabilities.
Okay, walk us through this minimalist toolbox. What's in there?
Well, first you have pi.
Of course.
Naturally, you can't have circles or spheres or waves without pias baked into the nature of space, so that's a given.
Okay.
Then they use integers. Simple, whole numbers, 1, 2, 14, 27, 108. They're very strict about this. Nature, they say, counts in whole numbers. You don't have half a quantum state or 2.7 dimensions in a crystal.
Pi and whole numbers.
Yeah.
Simple enough. I'm with you so far.
And then there's a third piece. This is the engine of the whole theory. They use a value they call nu dua. That's the Greek letter nu.
And news derived from the golden ratio, right? Which is where my skeptic alarm starts to go off a little bit.
No, I know. I had the exact same reaction because when you hear golden ratio, you immediately think of what? Da Vinci paintings or Nautilus shells or maybe some conspiracy theory on YouTube about the pyramids.
Exactly. It often signals numerology or pseudoscience, not hard physics. It feels a little mystical, like we're about to start talking about sacred geometry crystals.
I was deeply skeptical too. But in these papers, they aren't using it for aesthetics. They're not talking about beauty. They define the golden ratio, which is a fifth, about 1.618, and its conjugate, which is nu, about 0.618, as the benchmark for fractal efficiency.
Efficiency. Efficiency in what sense?
In a pure mathematical sense. The golden ratio is what's known as the most irrational number. What that means is it's the hardest number to approximate with a simple fraction. If you are building a system like, say, a universe that needs to scale infinitely from the very, very small to the very, very big without the frequencies and resonances crashing into each other.
Like an opera singer shattering a glass.
Exactly like that. You would use the golden ratio. It is the optimal engineering constraint to prevent resonance disasters in a fractal system. It's the ultimate shock absorber.
So it's not magic. It's just the only way to build a scalable system that doesn't shake itself apart over billions of years.
That's the argument. They claim Chernal is the fractal time constant of the universe. It's the fundamental frequency of reality's operating system.
Okay, so the claim is, using just pi, the golden ratio's conjugate, and a handful of integers, they can solve the biggest mysteries in modern physics. And they call this the quintuple crown of validation.
That's the audacious claim. They say the single unified geometric logic unlocks in one go. Dark energy, the Hubble tension, the muon G2 anomaly, the lithium-7 problem, and galactic rotation curves.
All the things that currently require us to invent invisible substances or just fudge the numbers with those parameters.
All of them at once with one geometric key.
That is a staggering promise. I mean, if this is even remotely true, it changes everything. So let's unpack this piece by piece. We gotta start with the foundation. Part 1. The new architecture of reality. You said earlier they think we've mistaken hardware for software. What does that actually mean when we're talking about the fabric of space and time?
Let's think about how we view the vacuum of space right now in the standard model. We treat space as a software layer. It's like a fluid or maybe a passive stage for a play. In Einstein's general relativity, space is a fabric. It bends, it stretches, it can ripple with gravitational waves, but fundamentally it's a container. It's passive.
The stage doesn't tell the actors what to say. It just holds them up.
Perfectly put. The Grimberg and Nexus theory, which they call the unified chronofractal field, or UCF, says no. That is fundamentally wrong. Space is not a smooth, continuous, passive fluid. Space is hardware. It is a rigid, discrete geometric structure, a lattice.
So we are literally living inside a crystal.
In a manner of speaking, yes, but an incredibly complex one. Specifically, they call it lattice 14.
Lattice 14? That sounds like a sector in a sci-fi movie, but I'm assuming the number 14 comes from that integer toolbox you mentioned.
It does. It comes directly from the mathematics of crystallography. If you want to stack rigid, identical structures in three-dimensional space to fill it completely, there are mathematically only 14 unique ways to do it.
Only 14.
Only 14. These are called the Bravais lattices. The theory posits that the vacuum isn't empty. It is a rigid geometric sieve that is saturated at the 14th iteration. It represents the most complex, most stable way space can possibly be organized before it just starts repeating patterns. It's the final form.
So everywhere we look, the air in this room, the space between the Earth and the Moon, the deepest, darkest void between galaxies, we aren't looking at nothing. We are looking at and moving through a saturated crystal structure.
A fractal crystal structure, yes. And this lattice isn't just sitting there passively. It actively processes information. And this brings us to a concept in the papers that I have to say really blew my mind. The fibit.
The fibit. That's phi, like the golden ratio phi, and then bit.
Correct. Fayabit. So think about standard information theory for a second. The fundamental unit is the bit, a 0 or a 1.
Right.
A bit is static. It's absolute. If I write a 1 on a piece of paper today, it's still a 1 in a million years. It doesn't change. It has no history.
Right, if it is the bit.
But the UCF says, hang on, the universe is expanding and it has a history. It's 13.8 billion years old. The density of this cosmic lattice changes over time as it expands, so a unit of information today cannot be thermodynamically identical to a unit of information from the moment after the Big Bang.
So information ages, it evolves.
It scales, it accumulates history. They define a fibit as a unit of thermodynamic information that scales with historical density, and they give a formula for it. 1 fibit equals 1 standard bit, multiplied by the term 1 idle text.
1 gigayear. A billion years to the power of nu, that fractal time constant.
Exactly. It connects information theory directly to the age of the universe. It says information isn't abstract, it's a physical property that's tied to the history of the hardware it's running on.
And the engine driving all of this processing is time itself. But as you said, not the time we're used to.
Not at all. This is the core axiom of the whole thing, fractal time. The source material states it very explicitly, almost like a commandment. Time is not linear, it is fractal.
What does that even mean for us? I'm looking at my watch, the second hand is ticking. It seems pretty linear to me. 1 second follows the next.
Locally, it feels linear. On our scale, it's an excellent approximation. But they argue that structurally, time has a dimensionality. They denote it as d-day. And the formula they derive for it is simply $1 plus nu.
1 plus nu?
Yes, since nu is about 0.618, the dimension of time is roughly 1.618.
Wait a minute. Time has dimensions.
Okay.
Plural. We usually think of space as having 3 dimensions, height, width, depth, and time as just having one single dimension, a line moving forward. You're telling me time has 1.5 dimensions. What is half a dimension?
It implies that time has depth, or pressure. It's not just a thin, infinitely fine line connecting the past to the future. It's more like a thick fractal tube. It has a structure. And because time has this extra dimensional width, it exerts a real physical pressure on the 3D space lattice it's embedded in.
Pressure. That sounds like a physical force.
It is. The math shows it creates a negative pressure, an outward push. And this is the first big aha moment of the entire theory. If time has this intrinsic fractal dimension, it naturally pushes outward on space. It forces it to expand.
Hold on a second. A mysterious negative pressure that fills all of space and pushes the universe to expand at an accelerating rate. You're describing dark energy.
Exactly. In the standard model, we look out at the universe and we see it's expanding faster and faster. We have absolutely no idea why. So we invented a placeholder. We call it dark energy, some mysterious, invisible fluid that fills the entire universe and pushes everything apart. We don't know what it is, where it comes from, or what it's made of. We just know we need it to make the math work.
It's the ultimate knob on that soundboard you were talking about, the biggest fudge factor of all.
It is. It accounts for nearly 70% of the universe, and we have no clue what it is, the UCF says. You don't need a mysterious fluid. You don't need a new particle or a new force. You just need to account for the geometry of fractal time.
So dark energy is just the stress of time passing, the mechanical side effect of the hardware running.
It is the geometric stress of time fractal expansion, with its 1.618 dimensions being distributed over the 3 dimensions of the spatial lattice. That's it. It's not a substance. It's a consequence of the architecture.
That sounds incredibly elegant, but elegance doesn't make it right. Does the math actually match reality? Because we have very specific measurements for dark energy, or at least its effects.
We do. The key number physicists are chasing is the equation of state, which is denoted by the letter dollars, specifically $2 for its present-day value. The standard prediction, what you get from Einstein's cosmological constant, says this number should be exactly negative 1.0.
Okay, negative 1.0, a nice clean number. And what does the UCF predict?
They calculate it from first principles, the pressure of time distributed over 3 dimensions of space. The formula is simply $1 plus.
Then what does that come out to?
It comes out to approximately negative over 0.794.
That is a very specific and a very different number.
Yeah.
Negative 1.0 versus negative 0.794. That's not a small rounding error.
It's a huge difference. And this is their first major kill switch for the theory. They are planting a flag right here and saying, test us. The Euclid mission, that massive space telescope launched by the European Space Agency, is designed with the primary goal of measuring this exact value with unprecedented precision.
So if Euclid's data, which is expected around 2026, comes back and confirms that the value is negative 1.0.
The Grimberg Nexus theory is dead on arrival. It's falsified. It's wrong.
But if it comes back with negative 0.794,
then the standard model is what's wrong, and this hardware audit is right. And they even point out that some recent data from other projects, like the Dark Energy Spectroscopic Instrument, or DSI, is already hinting at a value that's slightly greater than omega-1. They call it a thawing model.
So they aren't just retrofitting old data. They are making a very concrete, falsifiable prediction about future data. That's high-stakes science.
It's the gold standard. You have to be willing to be proven wrong.
Okay, so that's the edge of the universe sorted out, potentially. But dark energy isn't the only major crisis in cosmology. There's the Hubble tension. I've seen this in the news quite a bit.
Yeah.
It's the big fight over how fast the universe is actually expanding, right?
It is the 5 sigma headache of modern cosmology. And 5 sigma, for listeners, is the statistical threshold for a discovery. This isn't a small disagreement. It's a massive, statistically significant discrepancy.
So what's the problem exactly?
Here's the gist. We have 2 completely independent ways of measuring the expansion rate of the universe, which is a number called the Hubble constant, or H$. When we measure it using the cosmic microwave background, the CMB, which is like the baby picture of the universe from just after the Big Bang, we get a value of about 67 kilometers per second per megaparsec.
Okay, 67, the early universe measurement.
Right, but when we measure it locally in our own galactic neighborhood, using things like pulsing Cepheid stars and type Eos supernovas, what they call the late universe measurement, we get a completely different value. We get about 73.
67 versus 73. Those numbers are not close enough to be a rounding error. They don't even overlap.
No, statistically, they are miles apart.
Mhm.
And physicists have been tearing their hair out over this for years. Is the baby picture wrong? Is our local cosmic ruler wrong? Is there some new unknown physics happening that's changing the expansion rate over time?
What does the hardware audit say?
It says both numbers are correct.
How can 67 and 73 both be correct? That's not how numbers work.
It's what they call a topological parallax. It's an environmental effect. Remember, the UCF views the universe as a rigid lattice. We are here right now inside a galaxy. We are inside a saturated part of the lattice where matter is very dense.
Right.
The cosmic microwave background measurements, however, are looking across the vast, mostly empty voids of the universe where the lattice is relaxed and not stressed by matter.
So the ruler itself, the fabric of space, actually changes depending on whether you're in a dense galaxy or an empty void.
The volume scaling changes, yes. They argue that the presence of mass saturates the lattice and changes its effective geometric properties. The sources provide a very specific formula for this. Local measurements must be scaled by the square root of $1 plus nu I3.
There's that nu value again, a geometric correction factor based on the fractal time constant.
Always. It's the one and only tuning parameter. And here's the kicker. When you take the CMB value of 67, the measurement from the relaxed early universe, and you apply that geometric correction to see what it would look like inside our saturated local universe.
Let me guess. It becomes 73.
It hits approximately 74.93 kilometers MPC, which doesn't just get close to the local observations, it matches them almost perfectly. They call it an exact geometric solution to the Hubble tension.
It feels almost too neat. It's like discovering you were getting 2 different measurements because you were using a wooden ruler that swelled up in the humidity of our galaxy.
That is a surprisingly accurate analogy. The humidity is the baryonic matter density that's saturating the local lattice. So again, no new particles, no mysterious new physics, just correcting for the geometry of the environment you're in.
Okay, that handles the expansion problem, but let's look even further back in time. You mentioned the James Webb Space Telescope earlier, JWST. It's been breaking the internet for the last couple of years with these images of massive, well-formed galaxies that seem to exist way too early in the universe's history.
Ah, yes, the impossible early galaxies. This is a huge, huge problem for the standard model right now. We're looking back to what's called redshift 10 or 12, even higher. That's just a few 100 million years after the Big Bang.
Yeah.
And we're seeing these monsters, bright, massive, fully structured spiral galaxies with dust and heavy elements.
And they shouldn't be there, right? Gravity takes a lot of time to pull clouds of gas together to form stars, and then to organize those stars into a giant galaxy.
Exactly. The standard theory of galaxy formation says this is a slow, bottom-up process. Finding these mature galaxies so early is like walking into a hospital nursery ward and finding a fully grown adult with a beard and a mortgage sitting in one of the cribs. It completely breaks the timeline. It shouldn't be possible.
So what's the standard explanation for this? How are they trying to fix it?
Honestly, panic. Or, they're trying to tweak the galaxy formation models to say, well, maybe gas collapse is really, really, really fast under certain conditions. But it's a stretch. It feels like a patch. The UCF says, it's not the galaxies that are wrong. It's your clock that's wrong.
Chronofractal time dilation.
Here it is. Remember, time is the processing speed of the lattice. In the early universe, the lattice was much denser, more compressed. They argue it had a much higher fractal processing speed. Time flowed differently relative to our linear historical view.
So a year back then wasn't the same as a year now in terms of how much stuff could happen.
Not in terms of processing cycles, no. And again, there's a formula. The effective maturity of an object is equal to the linear time that's passed, multiplied by the factor $1 plus nu.
Where z is the redshift, how far back we're looking.
Yes. So the further back you look, the higher the redshift, the stronger this time dilation effect becomes.
Okay, let's run the numbers on that. What does that mean for our adult in the nursery ward?
It means that at, say, redshift 10, where the standard model tells us the universe is only about 450 million years old, the UCF metric reveals that the matter in that galaxy has actually experienced about 1.98 billion years of effective historical duration.
Wow. That's a multiplier of more than 4.
Roughly. So the galaxies aren't impossible at all. They're not babies. They just had nearly 2 billion years of fractal time to grow and evolve and form heavy elements, even if our linear clock says only 450 million years have passed.
That resolves the time paradox completely. The adult in the nursery is actually an adult. We were just misreading the clock on the wall.
Exactly. And again, no new particles, no new forces, just the geometry of time itself.
I'm definitely starting to see the pattern here.
Yeah.
Every single time standard physics hits a wall, a paradox, or a tension, the UCF just says, you're not accounting for the geometry of the hardware. But we have to talk about the biggest wall of all, the one that literally holds our own galaxy together, dark matter.
Part 3, the end of dark matter. This is where the UCF gets really aggressive. This is probably their most controversial claim.
We all know the basic story. Vera Rubin, back in the 70s, discovered that galaxies spin too fast. If you just count up all the stars and gas and dust we can see, there isn't nearly enough gravity to hold them together. They should just fly apart like a merry-go-round, spinning out of control.
Right. So to fix this, physics invented dark matter, a vast, invisible halo of stuff surrounding every galaxy to provide the extra gravity needed to glue it all together.
It's the halo.
It's the halo. It's the duct tape of cosmology. But the UCF makes a very bold statement. There is no halo.
But the rotation, the spin, the galaxy is holding together. Something must be providing that force.
They account for it with a mechanism they call baryonic saturation. The theory argues that we are fundamentally miscalculating how normal matter-baryonic matter interacts with the vacuum. They present what they call a master equation, where the velocity of a star is a projection of the visible mass, modulated by something they call historicity.
Historicity, is that related to the Fibbits and the aging of information again?
It's the same core concept. The idea is that a galaxy isn't just a pile of rocks and gas sitting passively on a fluid stage. It's a deep groove in the lattice, a groove that's been worn down over billions and billions of years. The vacuum itself remembers the mass that's been sitting there. This creates a geometric boost to gravity.
So the vacuum itself helps hold the galaxy together because the galaxy's been there for so long, like a rut in a dirt road that keeps a tire in line, even if the driver isn't steering perfectly.
That's a great way to visualize it, yes. The lattice itself stiffens and warps around the long-term presence of mass. And they back this up with what they call the master plot. This is one of the key papers. They took observational data from 175 different galaxies, a big database called SPARC, and they plotted the UCF prediction against the observed rotation velocities. And they claim a near-perfect 1.1 correlation without fitting any parameters for individual galaxies.
And that's the zero parameter part again, because usually dark matter models have to tweak the size and density of the halo for every single galaxy to make it fit, right?
Correct. It's a well-known issue. In standard models, you basically have to custom build the dark matter halo for each and every galaxy. It feels very arbitrary. UCF says no, the geometry is universal, one equation fits all.
That's impressive, but is there any actual proof that dark matter doesn't exist? I mean, maybe the lattice effect and dark matter both exist?
That's where they drop the hammer with what they call the fast bar paradox. This is the sixth crown of their validation, an extra piece of evidence.
Okay, tell me about the fast bars.
Galactic bars are those big rectangular structures of stars you see in the center of many spiral galaxies, including our own Milky Way. Now think about the physics. If galaxies were really surrounded by a massive, dense sphere of dark matter particles, a thick fluid of particles, that halo would create drag. It's a physical effect called dynamical friction.
It's like spinning a big spoon in a jar of honey.
Yeah.
The spoon is going to slow down pretty quickly.
Exactly. The bar acts like that spoon. If the dark matter halo exists, the bar should slow down over cosmological time. But our observations show that these bars spin fast. They don't seem to slow down at all. This is a known and, frankly, embarrassing problem for dark matter theories.
And the UCF solution?
The vacuum geometry of the lattice is frictionless for rotation. They describe it as being like superconducting rails, because there is no particle halo, there's no honey, there's no drag. The lattice drag, as they call it, vanishes for pure rotation.
So the bars spin fast simply because there's nothing there to slow them down. No honey.
No honey, just geometry.
It's persuasive. No halo, no drag, fast bars. It fits the observation perfectly.
And they even use this geometric approach to tackle the S8 tension, the clumpiness problem. The universe today is surprisingly smoother than our standard models predict it should be. Gravity hasn't clumped things together quite as much as the models say it should have. The UCF explains this with a simple topological damping factor, which they calculate as eta equals 1 pi.
So gravity's ability to clump matter is literally limited by the geometry of pi.
It's limited by the disk projection of gravity in the lattice. Basically, they're saying you can't pack the room messier than the fundamental shape of the room allows. Pi puts a hard limit on the clumpiness.
Okay, so we've covered the edge of the universe, the beginning of time, and the spin of entire galaxies. But usually, these grand theory of everything papers stay in deep space. They avoid our backyard because the data here in the solar system is just too precise.
It is.
It's easy to hide an error in a galaxy a billion light years away. It's a lot harder to hide an error when you're trying to land a rover on Mars to within a few meters.
That is absolutely true. Most fringe theories completely disintegrate when they hit the high precision data of the solar system. But the UCF authors, they do the opposite. They insist the most powerful proof is right here. This is part 4, the mesoscale. And this is where they propose their ultimate, undeniable kill switch.
The Mars time drift.
This is fascinating. They predict a very specific, very tiny frequency drift in the communication link between Earth and Mars, the signals sent and received by the Deep Space Network, the DSN.
Why Mars specifically? Why not the Moon or Venus?
It's all about entropy. Earth is a very high entropy environment. We have a massive, complex biosphere. We have tectonic activity. We have oceans. We have 8 billion people and all their technology moving around. It's informationally very dense and chaotic. Mars, by comparison, is a low entropy, mostly dead rock.
So they have different information densities within the lattice.
Exactly. And because of that, the theory predicts a chronofractal friction between these two frames of reference. The processing speed of the lattice is slightly different in the two locations, and they derive a calculation for this drift based on the 14th fractal iteration of the lattice. The number they predict is 68.8 microseconds per year.
That is a remarkably precise number. 68.8 millionths of a second every year.
It is. And that translates to a frequency shift of roughly 12.8 hertz in the S-band telemetry signals that NASA uses. They put it right out there, they say. If NASA goes back and looks at their raw data residuals over the decades of Mars missions and finds this anomalous drift, Standard physics is falsified.
And standard physics predicts zero drift, right? After you correct for all the known relativistic effects.
Correct. We already correct for general relativity time dilation due to gravity and speed with incredible precision. There should be nothing left over. UCF says there is 68.8 microseconds of anomalous time left over every single year.
It's a smoking gun.
Ah.
It's a tiny, tiny number, but it's not zero. If that drift is hiding in the data, the lattice is real.
And the thing is, there are already well-known anomalies in the solar system that we can't explain. The flyby anomaly is a perfect example.
I remember this from years ago. Spacecraft getting these mysterious tiny speed boosts when they swing by Earth for a gravity assist.
That's the one. Galileo, the Near-Shoemaker probe, Rosetta, they all picked up these small but significant unexpected velocity changes. Just a few millimeters per second, but enough to completely confuse the mission engineers. The UCF calls this an elastic lattice collision.
Elastic. Why is that word important?
They view Earth not just as a big gravity well, but as a mechanical rotor, or a gear that is physically spinning in the rigid vacuum lattice. When a spacecraft approaches at a very specific angle, it essentially hits the teeth of this rotating lattice distortion. The formula they derive for the energy kick involves a factor of 2.
And why is the number 2 significant here?
In physics, a clean factor of 2 often indicates perfect momentum conservation in a solid-state elastic collision. Think of one billiard ball hitting another and stopping dead, transferring all its momentum. Fluid drag doesn't give you a clean factor of 2. They claim this factor of 2 is proof that the vacuum is a solid metric, not a fluid.
And does the math work out? Does it predict the anomalies?
They claim it matches the observed anomalies for all the different flybys to greater than 99.9% accuracy.
That's very hard to ignore. And then there's the moon. You mentioned the lunar recession problem.
The paleotidal paradox. This is a known headache in geology. We know from measurements that the moon is moving away from the Earth at about 3.8 centimeters a year.
Right.
Standard theory says this is due to tidal friction, the ocean sloshing around on Earth, which slows our planet's rotation down and, through conservation of angular momentum, pushes the moon out into a higher orbit. But if you calculate that rate backwards in time...
The moon should have been touching the Earth way too recently for it to be 4.5 billion years old.
Way too recently. The models show they would have collided about 1.5 billion years ago. But geologists know for a fact the moon wasn't crashing into us 1.5 billion years ago. The Earth was fine.
So the standard model just doesn't add up.
It requires inventing very complex, some would say convenient, models of how ancient oceans and continents were arranged to slow down the rate in the distant past. It's messy. The UCF fix is much, much simpler. They say the Hubble flow, the expansion of the universe, operates locally.
Wait, I thought the expansion of the universe only happened on huge scales, between distant galaxies. I thought local gravity, like in our solar system, completely overpowered it. That's what I learned in school.
That's the standard textbook view, yes. The UCF says, no, the lattice expands everywhere, all the time. Earth itself and the moon's orbit are expanding due to this lattice saturation. They calculate an expansion of the Earth-Moon system of about 22.1 centimeters per year.
So the moon isn't just drifting away from us because of the tides. The very space between us is literally growing.
Exactly. This lattice drag or expansion effect accounts for the missing recession speed. It perfectly stabilizes the Earth-Moon history without needing to invent convenient ancient tidal models. The paradox just vanishes.
It seems like every single time there's a paradox or a tension or an anomaly in standard physics, this lattice theory just fits. It just slides right into the gap.
That's their central argument for what they call geometric inevitability. If you get the hardware schematic right, all the bugs in the software just disappear. But to really prove this is a theory of everything, you have to go smaller, much, much smaller. We've done galaxies, we've done the solar system. Now we have to go down into the quantum basement.
Part 5. The subatomic world. This is usually where these grand gravity theories fall apart. Quantum mechanics and gravity notoriously hate each other. They just don't play nice.
They usually don't. But the UCF claims to unify them through the shared geometry of the lattice. Let's note the muon G2 anomaly.
Right, the muon wobble. This has been big news from Fermilab. The muon, which is kind of like a heavy electron, it wobbles in a magnetic field slightly more than the standard model of particle physics says it should.
It's a 4.2 sigma discrepancy. In particle physics, that's huge. It's a clear sign that the model is missing something. The UCF derivation for this is so simple, it's almost insulting. They say it's dimensional damping, remember the lattice? They say the vacuum folds cubically at that quantum scale.
Cubically, you mean like 3 times 3 times 3?
Yes. 33L equals 27.7 as in 5. They claim the anomaly is simply the standard theoretical calculation divided by 27.
So divided by 27, that's it.
That's the entire claim. And when you do that, the result matches the Fermilab experimental data exactly. They argue that the standard model is missing the volumetric fold of the vacuum. We've been doing our math in a smooth, continuous world when we actually live in a discrete, folded world.
And they apply this same logic to the Proton Radius Puzzle, too.
They do. The puzzle is, why does the proton look smaller when you measure its size with a muon orbiting it compared to an electron? The UCF says it's metric compression. The muon is much heavier, so it couples more tightly to the lattice spin. The correction factor they derive is $1, and a purely geometric term.
And the Neutron Lifetime anomaly. The fact that neutrons seem to live longer when they're flying in a beam than when they're sitting in a bottle.
Volumetric vacuum drag. The kinetic neutrons, the ones moving fast in a beam, experience a tiny amount of viscosity or drag from the vacuum lattice, which slightly extends their lifetime. The factor for that, $1 plus 127 TPaw.
I'm seeing a pattern here. 27 again, pi again.
It's always pi, it's always integers, it's always geometry. Which leads us, finally, to the biggest one, the Holy Grail, the number 137, the fine structure constant.
The famous number, the physicist Richard Feynman called it one of the greatest damn mysteries of physics. It's a fundamental constant that tells us how strong electromagnetism is. It's roughly 1 over 137. Why is it 137? Why not 140? Why not 5?
Nobody knows. In the standard model, it's just a number we measure. We plug it in. It is the most precisely measured free parameter. But the UCF claims to derive it from scratch. They say it's the sum of the hardware core and the fluid phase of a lattice.
Okay, you have to break that down. How do you build the number 137 out of pure geometry?
The hardware core, they say, is 108. This number comes from a spherical projection, which brings in a factor of 4 times that cubic fold of the vacuum, which brings in the 27. So $4 times 27 equals 180 height.
Okay, 108, that leaves us needing about 29 more to get to 137.
Right. Then they add what they call the fluid phase, which depends on the fractal time constant, 101. The term is 18. And finally, there's a tiny damping term related to the dimensionality of the system, which is nu-phi-psi.
So you take 108, you add 18 divided by nu, and subtract a tiny bit,
Okay.
and you get 137.
You get 137.035970, which matches the official CODETA measurement, the best, most precise measurement humanity has ever made, to greater than 99.9999% accuracy.
That's spooky. They just built the most mysterious number in physics from scratch, using geometry and a few integers.
It suggests that electromagnetism isn't some arbitrary force with an arbitrary strength. It has to be that strength because that's the geometric efficiency of the lattice. It's the only way the crystal can vibrate.
And finally, gravity. Big G. The other great mystery. Why is gravity so ridiculously weak? It's 10 times weaker than electromagnetism. This is what physicists call the hierarchy problem.
The UCF answer is, again, simple. It's geometric leakage. Gravity is just the residual stress of the system. They calculate a massive damping factor of 56 bodes.
Where does a number like 56 bodes come from?
4 dimensions to 3 of space, 1 of time times the 14 fundamental lattice modes times naught pi. Gravity is what's left over after the fundamental forces of the lattice filter information through all 4 dimensions. It's the tiny leakage of the hardware.
So gravity isn't a fundamental force in the same way. It's more like the exhaust of the system.
That's the implication. It's the accumulated stress in the lattice.
This all brings us to their conclusion. They call it the diamond seal.
This is the author's way of saying the logic kernel is closed and complete. They emphasize the hierarchy again. You have inputs, like the speed of light, which is just a property of the lattice, which feed into the axioms, which then generate all the predictions. There are no free parameters to tweak. There are no knobs left.
And they highlight the human-AI symbiosis one more time at the end.
Right. They claim this unique collaboration was necessary to bypass the theoretical stagnation in physics. A human physicist might be afraid to say, the universe is a crystal, because it sounds crazy. It could risk their tenure, their reputation. An AI just looks at the data fit and the mathematical elegance and says, this is the optimal solution. It doesn't care about the politics of physics.
It's a fascinating glimpse into the future of science, maybe. The AI as the fearless co-author. But for now, for today, it all hinges on the final test. We've mentioned the kill switches throughout this.
Yeah.
Let's just recap them one last time, because this is where the rubber meets the road.
Absolutely. The 3 big falsifiable predictions are: 1, dark energy. The Euclid mission needs to measure the equation of state, $2 to be mana 0.794. If it's mana 1.0, the theory is over. 2. The Mars drift. NASA needs to check its decades of DSN data for an anomalous time drift of approximately 68.8 microseconds per year. 3. And a related one, Voyager 1. There's a predicted S-band resonance in its signal at 12.84 Hz caused by the same effect.
They are literally laying their cards on the table and telling the entire scientific community, here are the numbers, go check them. If we're wrong, we're wrong. But if we're right...
If they're right, then we live in a crystal universe.
So what does this all mean for you, the listener? Why should you care if space is a fluid or a rigid lattice?
I think it's a profound shift in perspective. We're used to thinking of the universe as a chaotic place, governed by random constants and filled with invisible fluids that we can't see or touch. The UCF paints a picture of what they call geometric inevitability.
It's deterministic, it's structured, it's hardware.
It implies that the universe isn't a simulation that's running some arbitrary code. It is the computer. It is a crystal structure expanding in fractal time. And we and everything we see are the processes running on it.
Which leads us to a final provocative thought to leave you with. If the fine structure constant and even the speed of light are just emergent geometric properties of this lattice, then is what we call time, just the fundamental processing speed of that lattice.
And if so, what happens if the lattice saturates? Does the processing slow down? Does the universe crash with a blue screen of death? Or does it crystallize into something else entirely?
Something to mull over next time you look up at the stars. Keep your eyes on that Euclid data release. It might just be the moment we find out for sure if we live in a fluid or a crystal. Thanks for diving deep with us.
Until next time.